In today's lecture, we are going to look at how we can solve about 5 multiple problems in Linear Algebra 2. All right, so our first problem is in V equals R4, we want to consider this subspaces U equals this, and A and B belongs to what? The real number system, and W equals this subspace, and C and D belongs to what? R. Now, we want to show that V is equal to what? U plus W. Okay, so first of all, what we have to consider first is that, in if they are saying that V is equal to R4, then considering the subspaces U equals what? A, comma 0, comma B, comma 0, right? Where A and B belongs to the real number system. Then, and W, right? W is equal to 0, C, 0, and D, where C and D belongs to what? The real number system, right? Then we can say that every vector that belongs to R, so we can say that every vector, okay, every vector V that belongs to what? The real number system, which is the R4, can be written as can be written as A, comma B, comma C, comma D, right? For real numbers. Okay? For real numbers A, B, C, and D. So every vector V that belongs to the R4 can be written as A, comma B, comma C, comma D for real numbers A, B, C, and D. Okay, so we can write this as well, can be written as, we can write that as A, comma B, comma C, comma D plus this A, comma B, comma C, comma D can be equal to, we can write it as A, comma, guess what? We are making sure that we get what is over here. So we can say that that is equal to what? A, comma 0, comma B, comma 0 plus 0, comma C, comma 0, comma D, right? So this is the same as this plus this, right? So once we have this, then don't forget that the first part is in the U, or okay, the first part is in the U and the second part is in the W. So we have to write all that. So the first part is in the U and the second part is in the W. Okay, so once we know that this is equal to this plus this, then we know that the first part is in the U, of which we have here, and the second part is in the W, of which we have here. So with that, we can say that V is equal to what? U plus what? W. That is very simple. We can say that V is equal to U plus what? W. Okay? So with U, the small u that belongs to what? The capital U, and the small w that belongs to what? The capital W. Okay, so this is just a short proof. Okay, this is just a short proof. So that is the end of the work. So therefore, we can say that every vector in R4 is in what? U plus W. So we can say that that's every vector in R4 is in U plus what? W. Every vector in R4 is in what? U plus W. So that's U plus W is equal to V, or V is equal to U plus W. They are all the same. So hence V is equal to what? U plus W. That's so hence proven as record. Hence proven as record. So this is the process. Don't forget that this one belongs to the real, where this A and B belongs to the real numbers. W is equal to this element, and C and D belongs to real numbers. So don't forget that every vector that V that belongs to the R4 can be written as A, B, C, D for real numbers A, B, C, and D. Okay, and don't forget that you can also write it as A, B, C, D, and that is equal to the U plus the W. It's all marked out to the same result, right? So the first part is in the U and the second part is in what? The W. So once we have these informations, then we can say that V is equal to what? U plus what? W, with small u in capital U and W, small w in what? Capital W. So that's every vector in R4 is in what? U plus W. So we can say that V is equal to U plus W. That's, or hence proven as record. That is question number 1. Let's move to question number 2. Okay, so with question number 2, we want to determine whether or not a particular vector V equals -9, 5, and -8 lies in U plus what? W. Okay, so this is how the question goes. Let's, in V equals R3, let W be the subspace consisting of all scalar multiples of U, right? And U is 1, 3, -4. And W be the subspace consisting of all scalar multiples of W, right? Which is 5, -1, and 2. Okay, so this is how the solution goes. You know, when you have a question like this and you want to determine whether or not the vector V -9, 5, and -8 lies in U plus W, then first, what you have to state first is that in V equals R3, okay, in V equals R3, then let U equals what? The span, right? The span, which is what? 1, 3, and 4. Okay, so, and also W equals what? The span, which is 5, -1, and 2. Okay, so once you state this information, the next thing you have to say is that to determine whether or not V lies in U plus W, whether or not V lies in U plus W, then first what you have to do is that take U, okay? Take U, then multiply it by a scalar, plus take W multiplied by a scalar. If these two results gives you the V, then you can conclude that V lies in what? U plus W, right? So we need to find scalars such that, scalars, let's say C1 and C2, such that V is equal to what? The C1 times the U plus C2 times what? The W, right? So we need to find scalars, okay? Say C1 and C2, such that C1 times what? U plus C2 times what? W should be equal to what? V. Right? So where is our C1? Our U is what? This. So we have C1 into what? 1, 3, like 4, plus C2 into what? The W is 5, 1, and 2. This result should be given as what? V. Okay, so don't forget that the U and the W belongs what? The V. So U and the W belongs what? The V. That minus 9, 5, minus 8 should be equal to what? C1 times what? 1, 3, 4, plus C2 times 5, 1, and 2, right? So this, we are going to use what? Matrix, right? To find the scalars C1 and C2. So we represent this in the matrix form. So the C1 will be on the first column, 1, 3, 1, 3, and what? 4. And then the C2 having this will be 5, 1, 2, multiplied by C1, C2, of course, equals what? 9, -9, 5, and negative what? 8, right? So we're going to use the Gaussian elimination to find out the C1 and the C2. Okay, so we move up here. We move up here. So we say that using the Gaussian elimination, uh, we can say that this here, 1, 3, 4, 5, 1, 2, multiplied by what? 9, 5, 8, right? So what are you going to do? Let's try to eliminate some of the elements so that we can find out the C1 and the C2. So let's say that root 2 should be equal to what? Root 2 should be equal to 3 times what? Root 1 plus what? Minus root 2, right? So, this is 3. So 3 times 1 will give you what? 3. Then this minus this will give us what? 0. So we're going to do that. Then we can have, okay, so we can also say that R3 should be equal to 4R1 plus R3, right? So we are eliminating this and we are eliminating this, right? So 3R1 minus R2 give us what? 0 here. And 4R1 plus R3 give us what? 0 here. So we're going to have 1, 5, then 3 times R1, which is 3, minus R2 is what? 0. So we have the R2 to be 0. Then here we are going to have 16, and we have here 0, we have here 22, and then we have -9, -32, and -44, right? So this is what we have now. Okay, so now that we have this, we can say that C1 plus C2 should be equal to what? C1 plus 5C2 should be equal to what? -9. Okay, then we can say that 16C2 should be equal to what? -32, right? 16C2 should be equal to -32. So we can say that our C2 is equal to what? Negative 2, right? So we have the C2 to be what? Negative 2. So we can put the C2 into what? C1 to have what? Uh, the equation 1 to have what? C1. Okay, so C1 plus 5 into what? Negative 2 equals what? Negative 9. So we have C1 equals what? Negative 9 plus 10, right? So we have C1 to be what? Positive 1. Okay, so now we have obtained the scalars, right? The C1 and the C2. So what we have to do is to multiply these scalars by U1, then the second one, which is C2 by W, to have to see if the sum will give us what? V. So we say that V, which is negative 9, 5, and negative 8, should be equal to C1, which is 1, times the U. The U was 1, 3, 4, plus C2, which is negative 2 of the W, which is 5, 1, and 2, right? So let's try to expand this and add it to there, see if we will get this, right? So we come here, we have negative 9, 5, negative 8 to be equal to 1, 3, 4, plus negative 10, negative 2, and what? Positive 4, right? So let's try to add this and this. So we're going to do that. 1 plus negative 10 becomes negative 9. 3 plus 2 becomes 5. Negative 4, negative 4 becomes negative 8, right? So this means that what we have here, negative 9, 5, negative 8, is equal to this, right? So this is indeed telling us that V is equal to what? U plus what? W. So we can conclude that since negative 9, 5, and negative 8 is equal to negative 9, 5, and negative 8, we can conclude that V is equal to what? U plus what? W, right? So V lies in what? U plus what? W. So we can say that that's V lies in U plus what? W. Right. So that is the end of problem number 2. Whenever you have two subspaces and you want to check if a particular vector lies in these two subspaces, multiply the subspaces by a scalar, right? Each subspace by a scalar. Then use the Gaussian elimination method to find those scalars. Now, once you have the scalars, use the scalars to multiply each of the subspace, right? Add the two subspaces. If they are equal to the vector, then it means that that particular vector lies in the summation of the two subspaces. And that's the end of the problem number 2. Okay, so with question number 3, we have this span, right? U equals this, and that is in R3. Such that u1 plus 2u2 minus 3u3 is equal to 0. And that of W is a set of all vectors. W equals this span, and that one too is in R3. So with W such that 2w1 plus w3 is equal to 0. Now we want to find the intersection between U and W. Okay, so first of all, this U as a span has been given as U equals U1, U2, and U3, right? has been given us, have been given such that u1 plus 2u2 minus 3u3 is equal to 0, and w of which is given this span w1, w2, and w3 such that 2w1 plus w3 is equal to 0 as well. So we want to find the intersection between u and w. So this basically means that we have to find all vectors, say v, right? Because v1, v2, v3, right? Such that these three vectors belongs to what? The R3. So this means that we have to find all vectors such that v is equal to what? v1, v2, v3. And these vectors are in what? Or belongs to what? R3. Okay. So first of all, what we have to do is we have to convert this to this one and this one into what? Equations, right? So we have v1 plus 2v2 minus 3v3 equals what? 0. Okay, and this name as equation 1. Then we have 2v1 plus v3 is equal to what? 0. So this is what? Equation 2. Now we have to solve these two equations, right? We have to solve these two equations and find the intersection, right? So what we are going to do is we still apply the Gaussian elimination method, right? So we are going to use the Gaussian elimination method, right? So here we represent this information in the matrix, right? So we have 1, 2, and -3. Then we have 2. The V2 part is not available, meaning it's 0. So we have 0 here and we have 1 here, right? And this has no constant because it is homogeneous, right? So this is not having any constant since it's homogeneous. So we're going to solve that matrix. So we can say that R1 is equal to what? 2R1 minus R2, right? 2 times 1 is 2 minus 2 to give us what? 0. So we want to make this portion to be what? 0, right? So we're going to say that this minus this is 0. Then we have 4, right? 2 plus 2, right? So that is 4. Then we have 7 here. Then we maintain the second row, right? We maintain the second row. Okay, so now that we have eliminated the V1, which is the first element, and the second element on the second row, then we can go ahead and put this thing in equation form, right? So we're going to have 4v2 plus 7v3 equals what? 0. Okay, so we have to say that one of the variables belong to the real number system. So we assume that v3 should be a constant, right? So let's say that, so this is equation 1. Then equation 2, we said 2v1 plus v3 should be equal to what? 0. That's equation 2. So let's say that v3 is equal to C, and C belongs to what? The real number system. Okay, so if C is equal to V3, then we can say that from equation 2, we say that 2V1 is equal to what? Minus C, right? So we have V1 to be what? Minus 1 on 2C, right? So from here, from here, from here, we can see that since C represent the V3, we have the V1 to be what? Minus half. So we have V1 to be what? Minus half C, and V3 is what? Minus C. And now we can look for V2. So we say that V2 should be equal to minus 7 V3, right? And V3 is what? Minus C. So we have V2 to be equal to what? 7 on 4, right? So 7 on 4, negative of that, right? So we're going to have the constant, right? The intersection to be, which is the V1, V2, and V3 to be, V1 is what? Minus half, right? And V2 is what? Minus 7 on 4. And V3 is what? Minus C. So we're going to have 1 here. Then we bring the C out, right? So we have the intersection to be minus half, minus 7 on 4, and positive 1. So that's that's the intersection of U and W is given as minus half, 7 on 4, and 1, right? This C belongs to real numbers, right? So the C can be anything at all. So that is what we have for question number 3. Very simple, right? So if you have two um, subspaces, right, and you want to find the intersection between these two subspaces, right, first of all, represent these subspaces in a matrix form. Okay, so once you represent these subspaces in a matrix form, you have um, 3 variables, right, and you have 2 equations. So more variables than equations. So you represent one variable by a constant. So by a real number, say C or any variable, okay? Then once you have that, you can determine the rest of the variables. Okay, so these values that you obtain for V1, V2, and V3 represent your intersection for this particular subspace. Right. So that's the end of the problem 3. Okay, let's move to the last part of the problem 4, where we have to determine whether this particular problem is a set of or constitute a basis for the vector spaces. Okay, then I'll give the last part as 3 minus 12 plus what? 9, and that is what? So with question number 4, we want to determine whether or not this particular set S equals this quadratic equation, comma, this quadratic equation, and this quadratic equation constitute a basis for the vector space P2. Okay, so once you have a set, a particular set of which we are asked to check whether it constitutes a basis for a vector space, say P2, what you have to note first is that Pn is equal to Rn plus 1, right? So first, note that Pn is equal to what? Rn plus 1, right? So here, we know that our n is what? 2. So we have 2. P2 is equal to what? 2 plus 1. So this implies that P2 is equal to R3. So we have to get what? R3. So we are working with what? R3, right? So first of all, say that V1 should be equal to what? The first quadratic equation, right? So that is x squared minus 2x plus 3. And V2 should be equal to what? Minus 4x squared plus 5x minus 6. And V3 should be equal to what? Minus 3x squared plus 3x minus 3. Okay, so these vectors, right, have a sub have spans, right? So we can see that this is 1, minus 2, and 3. And this is negative 1, negative 4, 5, and minus 6. And also this is minus 3, 3, and what? Minus 3. Okay, so first of all, this we have here, there are what? 3 coordinates in each subspace, right? So we can see that this is basically vectors in what? R3, right? Because we have 3 vectors in R3. So since we have the 3 vectors in R3, then we have to just find or show that it is what? Linearly independent. So if it is linearly independent, then we can say that it constitutes a basis for uh, the vector space P2. Okay, so let's say that this be our matrix, right? So we're going to have 1, neg 2, 3, neg 4, 5, neg 6, neg 3, 3, and neg 3, right? So this is our matrix that we derive out of this R3. Okay, so if whenever you have this kind of question, first of all, check if it is a square matrix. If it's a square matrix, then just find the determinant. If it is not equal to 0, then you can say that it forms a basis for the vector space. But if it is not a square matrix, then you have to use the reduction, the elimination, right? The Gaussian elimination or the Gauss-Jordan. But this is a square matrix, so we can just find the determinant and check if it is not equal to 0. Once it is not equal to 0, then hooray. So here we find the determinant of A. We are using the rule 1, right? So using rule 1 as our operation rule, we're going to have 1 into 5, 3, next 6, next 3, plus 2, because here is negative and there is a negative affecting the second part. So it's going to be plus. Then we have minus 4, minus 3, minus 6, minus 3. Then plus 3 into minus 4, minus 3, 5, 3. Right? So we're going to have 1 into minus 15 plus 18 plus 2 into minus this, and this will be plus what? Plus 12. And then we're going to have plus 18. But there is a negative here. It's going to be what? Negative 18 plus 3 into what? This will be what? Minus 12. And this will be what? Plus 15. Okay, so we can say that the determinant of A is basically equal to okay, so here we have 3 minus 12 plus 9, and this is 12 minus 12, which is what? 0. So we can say that since the determinant is equal to 0, since the determinant of A is equal to 0, then the vectors are not linearly independent. They are not linearly independent, right? So they are not linearly independent. Okay, so the given set is not a basis, it's not a basis for B2, right? It's not a basis for B2 because the determinant of A is 0. Okay, so that is question number 4. Now let's move to question number 5. That one is going to be a trial. For question number 5, we have been given these vectors, okay? P1 of x equals this, P2 of x equals this, and P3 of x equals this. And we want to determine whether or not the sets, right? P1 of x, P2 of x, P3 of x is linearly independent. Okay, so same approach as question 4, okay? Since there are 3 variables, right? And they will form, it will be Pn equals what? Rn plus 1, right? So this one, you're going to have 3 subspaces what in R3, right? So you can use the determinant approach, right? So it's going to form a square matrix. So we just find the determinant. If the determinant is not equal to 0, then you can see that it's indeed a linearly independent uh, vector, right? So go through that process, and if you get it, just drop your answer at the comment section. Thank you very much for watching. I really appreciate your time. Please don't forget to subscribe, share with your mates, and keep learning. Until the next video, stay inspired. Bye bye.